Welcome to this new video on the journey of performance-based design. We actually mean the journey of the performance-based seismic design. In this video, we shall be seeing how, on a chronological way, the journey of the performance-based design went ahead and what are the different outcomes at different stages and what is the final stage at which now we are standing. So let us give a definition to the performance-based seismic design. One definition given is FEMA 445, which states like this: the performance-based seismic design process explicitly evaluates how a building is likely to perform given the potential hazard it is likely to experience, considering uncertainties inherent in the quantification of potential hazard and uncertainties in the assessment of the actual building response. So they have written it as a design process. So we have to look into the design process. We have to evaluate the design process, and we have to know the new design process. And it is there telling the assessment of the building performance under a potential hazard which the building is likely to experience, and it is considering the inherent uncertainty in the potential hazard and uncertainty in the building response. Okay, I give a definition here, a small definition. The performance-based seismic design is a design method which sets design objectives prior to design to be achieved under some given hazard level. So this definition is simpler. We have some design objectives which are set prior to the design, which is not done in the codal design methods, and this is to be achieved under some given hazard level. So hazard level you can take to your requirement, and the design objectives also you can set to the requirement of the customer or the functional use of the structure. Now question is why we should go for PBSD. Codal designs are force based, because you have seen in my previous videos the code actually gives you a base shear formula based on certain parameters like seismic hazard level Z and the importance factor and the spectral acceleration ratio and the seismic weight of the system. So ultimately it is giving a force, and for that force you are designing it, and you do not know how your building is going to perform when an earthquake comes. So performance of the building remains in cloud when you use the codal design method. Our aim in the design is to minimize the damage. Now minimize the damage, when we say it may not be absolute scale. We may want some damage in certain structures of less importance, and we may want very little damage in structures which are very important. So we can make a decision about how much damage we are going to allow in the system. This is not possible in the codal design. And damage means it is a function of displacement. Damage means some nonlinear displacement, nonlinear rotation, nonlinear linear displacement, nonlinear twist, nonlinear strain, and so on. So these are all displacement functions, generalized displacement functions. So since damage is a function of displacement, why not design for the displacement so that you are designing for the damage? Why to depend on the force as is there in the current codal design? In the codal design, it is difficult, if not impossible, to design for target design objectives set prior to design. Suppose a simple example we take: I want to design a building for 2% interstory drift. So no code in the world, unless it is following the performance-based seismic design procedures, will be able to give you a procedure so that you can attain 2% drift. What you can do, you can follow the codal design as given in the code as prescriptions, and finally check whether 2% drift is obtained or not. If not obtained, you make another iteration, and you do not know how many iterations will be required, maybe hundreds, before you achieve that 2% drift. So in the codal design, it is not possible to set your target design objectives a priori. In codal design, seismic level is not in the hand of the designer. It is given in the design spectrum of the code, and you have to use the spectrum, and depending on the zone where your structure is situated, you have to follow the seismicity level of that zone. Now I may want, going out of the bound of the code, I may want a building which is very important, say hospital building. I want to design it for a higher seismic hazard, so code will not permit it. I want to design a hospital building for very stringent performance levels, so these are not even stated in any code. So these are the limitations we are finding. All the limitations, and you can check our previous videos where we have discussed the force-based design. All these limitations are overcome in the performance-based seismic design of structures. Now, seismic codes are available for almost all the countries, saving one or two small countries, and mostly we are still following the codal design procedures. But gradually a shift is being seen now that some countries are shifting to performance-based design. For example, in American ASC 4117 code, the performance-based seismic designs have been incorporated more or less. Similarly, in some countries it is available. So the future design world will be performance-based, and present design world is gradually shifting to PBSD. So these performance criteria are the different motifs of the structures which we want to satisfy to fulfill the need of the structure. For example, what is the drift? What drift causes what effect to structural elements? So if we take say 3% drift, then what is the consequence over the elements? So now drift is a performance objective, and the effects it is making on the structure are the performance criteria. Suppose it makes some cracks, suppose it makes some damage of the non-structural components. So those are my performance criteria, and drift is a performance objective. So through this drift I shall be checking the performance criteria related to the effect of drifts. Then what crack width is allowable in an environment? What drift is allowable for a particular type of equipment? Certain equipment are drift sensitive, certain equipments are acceleration sensitive. So if it is drift sensitive, you have to restrict the interstory drift of the building which is housing the equipment. At what drift a particular type of cladding cracks? A cladding in the building may be made of glass, and the glass has the tendency of cracking if the interstory drift between the stories is high. So you can check those limitations and you can decide about the drift amount for that claddings. Similarly, for other claddings other than glass, there will be certain limits at which they will start cracking. What acceleration is given, equipment can withstand. So some equipment, as I said, are acceleration sensitive. So you have to decide what acceleration the equipment will be able to withstand, and then in the design you can take measure about that. What extent of plastic deformation is tolerable for a structural element? So it depends on the functionality of the structure. If it is a hospital building, I'll allow very small plastic rotation in the beams and perhaps no plastic rotation in the columns. If it is a residential building, then those corresponding plastic deformations can be of higher order. So these all will form your performance criteria over which you will decide your performance objective, and you will try to fulfill the objectives. So what are the performance objectives? What drift can be allowed for the structure depending on its functionality? Is it a residential building? Then what drift you allow? If it is a hospital building, then what drift you allow? Certainly drift will be less in the hospital building than in the residential building. Then other than building structures also, there will be some limit on the drifts. What amount of plastic deformation is tolerable for a structural element depending on its functionality and importance of the structure? Some structures are more important, some structures have post-earthquake importance, like firefighting buildings, water supply systems. Those are having post-earthquake importance. And certain structure which may produce hazards in the post-earthquake condition, those are also important for us, and we have to take special care for them. So based on all this, you have to decide your performance objectives which will be rendering you a structure to your desired goal. Now, under what hazard level you want those performance objectives to be satisfied? Suppose I want 1.5% drift in a building. Then question arises, under which earthquake? So hazard level you have to quantify. Now future earthquakes are not known to us, but we can have some idea studying the past earthquakes that what is the expected level of earthquake for that geographical zone, and also which return period we want to see in the earthquake. High return period earthquakes have greater intensity, greater shaking level. So if we are designing a building, certainly it has to be designed for a lifespan of about 100 years, and the return period you may consider say about 2000 years or so. So high seismic level. So based on the functionality of the structure, based on the importance you feel to be attached to the structure, based on its post-earthquake importance, and based on the consequence of damage of the building in the post-earthquake scenario, you have to decide the hazard level. And hazard level, how we designate? In terms of the fraction of G. So say 0.36 G, 0.45 G, 0.6 G. These are designating different levels of seismicity which are to be superimposed over the design spectrum. So you'll certainly design for the design spectrum of the country, and then level of the shaking you can change by taking the scales like this. So this hazard level is an input, as the input is the objectives, the design objectives. And design, if you want multi-objective design or multi-hazard design, what does it mean? Multi-objective means under low seismicity, my structure should be linear, no damage. So this is one objective. At high seismicity, my structure may undergo some plastic deformation to some limit that I want. So if these two we are considering a low seismicity, high seismicity performance, then we are having here two objectives. Similarly, when we said low seismicity and high seismicity, we are considering multi-hazards. If you look at our previous video, we have discussed this multi-hazard, multi-objective design. So depending on this, you can same structure should satisfy more than one objective at more than one hazard levels. What are target design objectives under what hazard level, that you have to decide in the system. Then after deciding the design objectives and the hazard levels, you have to now decide some engineering procedure for design. So these are established design procedures available in the literature. This should be sound procedure and which shall be able to satisfy the design objectives you have set. So there are certain methods available like direct displacement based design, DDBD. You have the unified performance based design, UPBD, and you may have more than these methods. So based on your need and based on the academic background, you can select some method of engineering design for the structure. Then after the design is over, you have to evaluate the structure because you have started with some design objectives at certain hazard level. So you have to demonstrate after design that your structure is actually able to sustain that hazard level and give you the targeted design objectives or not. So the means for this evaluation is pushover analysis, nonlinear time history analysis. For nonlinear time history analysis, we require spectrum compatible ground motions because we have designed at certain spectrum at certain hazard level. So the earthquake under which you test the system after design also should be of that same seismic level and matching to that spectrum. So this is achievable by taking ground motions which are called spectrum compatible ground motions. For generating these spectrum compatible ground motions, you have many software like Sysmomatch, also SEP 2000 ETFs also give such spectrum compatible ground motions. You require some background earthquake as a prototype earthquakes for generating these spectrum compatible ground motions. So while selecting background earthquakes, you may check the near field conditions, far field conditions, earthquakes, and you can check the available documents like P695, which will tell you how many ground motions to be considered and which kind of ground motions to be considered for your structure. So this is the evaluation of the structure. After evaluation, if your structure is all right, then you can forward to the customer. Otherwise, you have to redesign it. So you have to check whether drift is within your limit of target, whether the actual performance level is within the desired range that you decided. And if not, you have to redesign it. So that is what we are doing. Generally, in certain types of designs like direct displacement based design, you may require this iteration for design. In the unified performance based design, the member sizes are already known and it does not require iteration generally. So these are the basic two types of design we shall be seeing slightly in this video and on details in coming videos. Now let us see the chronological development of performance-based seismic design PBSD. In the beginning it was in all cloud. It took ages to understand by mankind that earthquake produces some horizontal force in the structure, because people used to see that any structure they made got damaged or collapsed under earthquake, but they didn't know what was the reason. So after applying intuition, they understood that it is producing horizontal force which is shaking the structure and it is causing damage to the structure. So how much force it is producing so that I can design for that force, that question arose. So initially it was suggested that 10% of the seismic weight of the structure can be taken as the lateral load for design purpose. In 1908 Messina earthquake in Italy, a commission was formed which gave a method of earthquake resistant design which is known as equivalent static method, which is there now in many courts. In 1914, a Japanese engineer named Sano proposed a method which is now known as seismic coefficient method. So you can see here in around this time, 1908, 1914, more serious thought was towards seismic design, and gradually the things evolved through research and application. 1927 Uniform Building Code was adopted. 32-33 Maurice Biot gave the concept of response spectrum, which is now part of all design course. He gave this concept in his PhD thesis. 61 John Bloom. You know there is a laboratory called the Bloom Laboratory. So John Bloom suggested reserve energy technique, and this was the pioneering concept behind the current capacity spectrum method. 1975 Freeman et al. Gave an evaluation procedure for a actual real project, and this is start of the capacity spectrum method. 1976 Park and Polle evolved the capacity design method. This we have discussed in previous video. Here we intend that certain members may fail in certain mechanism, in certain nonlinear hinge formation, and certain members should not form the hinges at all. So this is done through the capacity design. In 78 Freeman used the performance-based design as a procedure to correlate earthquake ground motions with observed building performance. 1980 ATC 10, the beginning of the PBD was used to procedure to find correlation between earthquake ground motion and building performance. 87-89 Faspar and Fissinger developed the N2 method. This is similar to your capacity spectrum method but in the initial stage. 1991 Kai and Noel gave the displacement based design. So here entered the displacement instead of the force. 92 direct displacement based design, which is very famous till date, was given by Polle and Priestley. DDBD method. 96 ATC 40 version of capacity spectrum method was given. This we have discussed in our previous video. 97 FEMA 273 document was introduced. It gave the backbone curve, which enabled us to correlate the static pushover with the dynamic forces, earthquake condition. 1998 multimodal pushover analysis was given by Sasaki et al. 1998 tri-services manual was introduced on earthquake design. 1999 SIOC Structural Engineering Association of California Blue Book 2000 was introduced. 2000 FEMA 356 is very famous. 2000 again Esteban Black developed yield point spectra. What is this? We are using the design spectrum which is based on linear design spectra, linear response spectrum, where the single degree of freedom system you have considered is linear. But if the single degree of freedom system has nonlinearity, then it will lead to what is called yield point spectra or nonlinear design spectrum. 2001 FEMA 368 for new building was introduced. Earlier, all the documents 350C etc. were meant for the rehabilitation of existing buildings. So first in 2001 368 was introduced for new buildings. 2001 model pushover analysis was introduced by Chopra and Goel. 2001 adapted model pushover analysis was given by Gupta and Kurnath. 2002 modified model pushover analysis MMPA was introduced by Chopra et al. 2004 incremental response spectrum analysis was introduced by Adinoglu, and this gradually led to your incremental dynamic analysis etc. and led to the fragility analysis. 2005 direct displacement based design for RC frame buildings or perimeter enclosed frame buildings was given by Pettinger and Priestley. 2006 by two papers direct displacement based design for dual system, that is frame shear wall system, was given by Sullivan et al. 2006 FEMA 445 next generation performance based seismic design was introduced. 2008 unified performance based design method for dual system was given by Choudhury. So these two methods we shall be emphasizing in this video as well as in the coming videos, the DDBT method and the EPBT method. 2012 DDBT method for frames with fluid viscous dampers given by Sullivan and Lago. 2013 Choudhury and Singh introduced EPBT method for RC frame buildings. 2014 Mayanbang and Choudhury introduced column size determination in the spectrum of displacement based design. 2015 EPBT method for steel buildings was introduced. 2017 local building code based on PVG was introduced in Mexico City. 2019 effective stiffness on seismic analysis and performance of buildings was given in a research paper. 2020 EPBT method for bridge piers was given. 2020 FEMA P20821 NERSP recommended seismic provisions for new buildings and other structures were introduced. 2021 Das et al. Gave effective stiffness of columns through genetic algorithm. There is effective stiffness we have considered in our previous video. In RC buildings, the effective stiffness is different from the gross stiffness. So what should be the value of the effective stiffness? That study is made in this paper. So 22 EPBT method applied to elevated water tank staging. So we have two methods as we mentioned earlier. One is direct displacement based design method, another is unified performance based design method. So in the direct displacement based design method, the design target objective is set in the beginning in the form of drift. The design displacement is found by applying the dynamical equations. So this method takes only one design objective, only drift. There can be more design objectives, but it is not able to consider any more design objectives in the design principle. Then unified performance based design method, we shall be discussing this in separate video. This method can accommodate two design objectives. This is drift and performance level. So this is now certainly a wider and more generalized concept of performance based design, and we shall be discussing this in detail later. This method also gives the member sizes. Very important thing, the earlier method, DDBT method, did not give you member size, and it was to be found by iteration or intuition, and the iterations was required to improve the sections. This EPBD method gives the member sizes in the beginning of the design so that iterations are almost not required. One word of caution here: the journey I have shown for the PBSD is seen through my own lens. So if you check it through the lens of others, it may look different, especially about the tail part of the journey. Thank you very much for coming up to here with me. Please subscribe the channel, like and share the video. Put your queries and your personal observations in the comments.